The second module is a time domain representation of LTI system. This LTI represents linear time invariant system. In the properties of system, we came to know that what is our linear. When a system is going to be told as a linear, it has to satisfy superposition theorem and also of the homogeneity. Then what about the time invariance? The system which is not going to vary with respect to the time. That is what your time invariant system. Now we'll going to learn about the system. The system definition will be taken like this, right? Input we are going to give as x of t, and you will be having the system. The system operator, what we taken? Sometimes we taken as h, right? And sometimes we taken as t of with flower bracket. We taken as like this, t of x of t we taken, right? That's what the system operator, and you will be getting as the output. In this, we are learning about the system, that is, which is linear and time invariant. That's what LTI system. In many of the application, what we are going to use in the LTI system, the main applications in terms of your communication way, it may be in terms of your robotic system, wherever the signal is going to be used, okay, in weather forecasting, in any of the application where we are going to use that. If I am choosing any of the device, it may be amplifier or anything which has to accessing the signal, we are mainly focusing that the system should be in a linear, that is very important, and it should not change with respect to time. For the reality, if I go for, it's always changing with the time, because it's for a second the weather will be changing. Yes, we have to making some constant values, taking an average values of those, then we will be finding of the what is the weather forecast. Okay, we are with a particular time we are going to access the signal. Okay, that's why it is very important to learn about LTI systems. Okay, just go with the theory what it's given in the textbook way. Okay, the systems which satisfy linearity and also time invariance are going to be called as linear time invariant system. The different time domain representations for LTI systems, that is representation that relate to the output signal to the input. Yes, this is if I take LTI system, the input and output when both the signals are represented as a function of t. Observe here, x of t is there and y of t is there in terms of continuous, but if I go with the discrete time, it's of x of n and y of n signal. Yes, then LTI system exhibits superposition property. Yes, from the linearity if I am going for, it should satisfy the superposition theorem. Due to this, it is possible to represent the input to an LTI system in terms of linear combinations of set of basic signals. Why it is taken as set of basic signals means, when I am going to represent my x of signal, what is the linearity it should satisfy means, when I am going for a part of the x of t signal, that is taken as x1 of t plus we are going for taking with another weighted with the bay taken as x2 of t, right? When this satisfying, then we are telling it's of a superposition. Linear combination, it's a combining both the signal, that is x1 of t with x2 of t with weighted some parameters, that is a and b, we call in terms of a coefficients. When we go in further topics, we will be learning of what is this a and b. Okay, this different signals if I add, I should get signal, it is also should be a linear one. Okay, that's what linear combination of set of basic signals. These basic signals, that is x1 of t and x2 of t, it may be of your unit step signal or else a ramp or else your impulse. Okay, we don't know. That's what here it is taken, the basic signal. Then it is also possible to find the output of the system in terms of the response to these basic signals. This is what the theory is given. Next topic is a impulse response representation for LTI system. What is the impulse response we come across? That is delta of t. This is a impulse function, right? How I can use this delta of t to the x of t input signal. This delta of t here we are going to take as a system function. Okay, how it is going to be done? We go through here. Next, a complete characterization of any LTI system can be represented in terms of its response to an unit impulse. Means the x of t signal if I am going to take x of t signal, I can represent x of t signal in terms of the delta of t signal. How it is going to be? With the example further I will be going to explain this. Okay, this is, you just remember this point, which is known as impulse response of the system. Then the impulse is the output of the LTI system. Impulse response is the output of the LTI system due to an impulse input that is applied at t is equals to 0 or n is equals to 0. Where is our delta function is going to be existing? At the 0th position only it is going to be existing, right? When it is at 0, our delta function, it is going to be existing. In terms of continuous, it is like this. If I am going for in a discrete way, it is of a magnitude is going to be 1. Here we don't know, based on the signal it is depending. Okay, that's what here it is taken. Then if the input to the linear system is expressed as the weighted superposition, weighted means multiplying the a into x1 of t, how much you are going to giving the amplitude for the signal. Okay, this is weighted, how much the weightage you are going to put for the signal. Weighted superposition of time shifted impulse. Then the output is weighted superposition of the system response to each time shifted impulse. Means when if I am going to change the time for t minus 1 at x of t signal, the output what it is going for, it is also shift by t minus 1 also. That's what the superposition theorem is going to be telling. Weighted, how much you are going to multiply in terms of a amplitude, in terms of a time, what you are going to change for the input, that same should satisfy at the output also. Okay, that's what we have to take here. Then if the system is also time invariant, then the system response to a time shifted impulse is a time shifted version of the signal of the system response. If it is time shifting, time invariant means it is also time invariant, it should satisfy. To the time shifted impulse is the time shifted version of the system response to the impulse. Okay, then the output of a LTI system is given by weighted superposition of the time shifted impulse response. Remember, weighted superposition of the time shifted response. That's for the output of the LTI system. This weighted superposition is known as, this superposition we are calling by the name, that is convolution sum for the discrete time signals and convolution integral for continuous time system. Remember, the weighted superposition is going to be called as convolution sum in terms of discrete time and convolution integral in terms of the continuous time systems. Then the representation of discrete time LTI system in terms of the impulse response. LTI system in terms of impulse response, how it is going to be represented. Here, considering one example, you can go with the continuous time also, but when I'm going for continuous, some extra knowledge should be there. For that reason, if we go with a discrete time, it will be easy to understand. For that reason, here it is taken as discrete time signal as an example. Here x of n signal it is given. It is having the samples at -2 with the weight of -1, at -1 as 2, and at 0 it is having 2, at 1 1 and 2.5. This is what the signal it is given. This signal is going to be represented in terms of delta of n function. This is in terms of discrete, for that reason it's taken as n here. The x of n signal can be shifted as shown. Just you observe here, x1 of n, I'm taking the first sample here, that is x, this is the x of -2, x of -2 is of -1, that's what x of -2 into delta of n plus 2. What is delta of n plus 2? If I draw, what it's going to be? Here you will be getting, if I multiply, what is the delta of n plus 2 actually? It's going to be at, delta function is going to shift at 2 position towards the left side. Means at -2 you will be getting your delta function only of this part. Then multiplying with the x of -2, x of -2 is of -1. If I multiply, you will be getting at the only one sample. You will be getting this sample as it is. So I can get only this part. When I take, just picking each and every samples here, just pick that and multiply with the delta function with the how many time it's going to be reflecting here. Okay, that's what here it is written. If I do this, I'll be getting the only of this part. Remaining part it will be 0 only. Okay, then I'm going to choose for the next sample, that is -1. That is x2 of n. It is going to be x of -1 delta of n plus 1, because here it is going to be n plus 2. It is shifted by 2 position towards left. Next, n plus 1, it is shifted by 1 position, for that reason. Okay. Then what I will be getting? I will be getting the next sample, this sample. Okay. Next, we finished off x1 of n, x2 of n, then x3 of n at the 0th position, means x of 0 delta of n. Delta of n means at the 0th position only you will be getting the sample. Here you should not go for arrows here because it's of a discrete time. Okay, this is your n and this is your delta of n. Okay, this is what you will be getting. Next, we go for the export of signal. How many signals are there? Just based on that samples we are going to take here. Then x4 of n is the next sample, x1, x of 1 delta of n minus 1. Okay, then here what's the signal you will be getting? The next signal. We finished off this also, and next is of at 1 position 1. X of 1 delta of n minus 1, because it shifted towards right position, for that reason. Then you will be getting this signal, and the last signal is of x5 of n, that is going to be x2 of n delta of n minus 2. Okay, x2 of delta of n minus 2, you will be getting this signal. Observe here, the x of n signal, it is there, but we represented the x of n signal in terms of an impulse for each of the samples. That is what we taken different signals, that is from x1 of n to the x5 of n. When I add all the signals, that is x1 of n, x2 of n, x3 of n, and x4 of n and x5 of n. Am I able to get this signal? Yes, I can. Yes. So I can write the resultant signal as x of n. I'm adding all the signals again. Okay. Here it is taken as x of minus 2 delta of n plus 2 plus x of minus 1 delta of n plus 1 plus x of 0 delta of n plus x of 1 delta of n minus 1 plus x of 2 delta of n minus 2. What we here it is written the same thing, we added all. When I add, it is able to get my x of n signal. So in general way we can write as x of n is going to be equals to, because it's of a summation, because it is discrete time, for that reason summation k is taken any variable here. It's not that you have to take only k varying from minus 2 to plus 2, x of k, here it is changing, observe here, minus 2 to 2, for that reason k, x of k, delta of n is remaining same here, then delta of n minus k. In general I can write here. Why we have to write the general equation here? Here we have taken only of 5 samples, but in general applications there are continuously coming where we are going to convert the analog signals to the discrete values. It's not having only 5 samples. It's a continuous samples. It's going to be processing in the processor. Okay, those processing and all you will be learning in higher levels. Okay, just remember how it is going to be taken. Then in general, this is what we taken for only for the 5 samples, but if I take for the infinite samples, okay, in general way, for a discrete time signal, x of n can be written as summation k is varying from minus infinity to plus infinity, x of k delta of n minus k. Here x of n as weighted sum of time shifted impulses. Yes, observe here, time shifted impulses, delta of n shifted by 2 position towards left, here also by left by 1 position, it is at the center, then here it is of right shifted by right position with 1, shifted by 2 position at the right side. That's what in the theory also we taken shift time shifted version. Weighted means how much the x of minus 2, here x of minus 1, the weighting, what is the amplitude it is having the samples, that's what weighted sum of the time shifted impulses. Okay, then I can go with the deriving part. Consider a discrete time LTI system. Here we are going to consider that is x of n, it is an input, a system, that is here it is taken as t operator, t with a square bracket, here it may be anything. Okay, then you will be getting the output as y of n, where x of n is the input to the system, y of n is the output of the system, then t of is system operator. Then what I can write here as the where the system is going to be processing based on the input what we are going to apply. For that reason, the output I can write as y of n is going to be t of x of n. This operator, which operation you are going to perform for the x of n signal. Then y of n is going to be, what is our x of n? We derived how it is going to be taken. That is x of n is going to be taken as this equation. You just substitute here. K is varying from minus infinity to plus infinity, x of k delta of n minus k. Okay, close this bracket. Then using of linearity property, what I can write here, y of n is equals to this time operator I can apply for the only for the impulse response. Okay, because here it is going to change the time only changing. Okay, if I take with the amplitude part, it's not a constant way. Time it may be shift by 2 position, 1 position at 0 position. Okay, for that reason only for the operator at impulse it is going to be applying, not for x of k. Okay, y of n is going to be summation k is equal to minus infinity to plus infinity x of k t of delta of n minus k. What is this? We call t of delta of n minus k corresponds to the operation of the system performed on time shifted impulses. Which operation we are going for here? Time operation we are going to be doing here. That's what time shifted impulse delta of n minus k. Therefore, what I can write here of delta of n minus k is going to be taken as h of n minus k. Okay, remember this point. I can write t of delta of n minus k as h of n minus k, where h of n is the impulse response of the system. Now onwards, remember, if I am going to talk about the impulse response means you have to remember this h of n. Impulse function is of delta of n. Impulse response, which is giving some response, shifting of the signal. It may be scaling of the signal. If it is going far, then it is of x of n signal. Okay, that is therefore what I can write. Y of n is going to be summation k is equals to minus into plus infinity x of k h of n minus k. This, remember, this is like a formula for you for the convolution, that is y of n. This is I can write as y of n is equals to x of n. This symbol, it's a star. This star we call as a convolution of x of n, convolution of h of n. Okay, the output of an LTI system is given by a weighted sum of time shifted, here it is of time shifted, h of n minus k is of a time shifted impulse responses, and the equation is known as convolution. Here we are taken as, for the discrete it is of convolution sum. In the theory part we come across. If I am going for continuous, it will be of convolution integral. Okay, this is just remember the equation, how we got this equation. It may ask sometimes in the exam for 4 5 marks, 6 or 5 marks. Okay, next we'll go for what we derived. It is for the discrete time. In the same way we will derive the equation for the continuous time. Here the representation for continuous time LTI system in terms of impulse response. In this, any arbitrary continuous time signal, that is x of t, can be expressed as a weighted superposition of time shifted impulses as x of t is going to be, we come across these parameters how it is going for, just taking the equation here. X of t is going to be integration minus infinity to plus infinity x of tau. Here it is taken with a different variable, that is tau, x of tau delta of t minus tau into t tau. Now consider a continuous time LTI system. Here it is going to be changing as x of t as the input with the operator t with t operator, then output is of y of t, then x of t is the input to the system and y of t is the output of the system. T operator is the system operator. Then what I can write, y of t is going to be t of x of t. It is same as what we done in the previous. Okay, then y of t is nothing but, what is our x of t? We take on this equation. Okay, directly you substitute here, that is we will be getting as integration minus into plus infinity x of tau delta of tau d tau. Then using linear property, where we are going to apply your operator for the impulse response only, impulse function only. Y of t you will be getting as integration minus infinity to plus infinity x of tau. Here you are going to apply the operator, that is t of delta of t minus tau into d tau. Then we are changing for this function, that is t of delta of t minus tau corresponds to the operation of the system performed on time shifted impulse, that is delta of t minus tau. Therefore what I can change here, therefore t of delta of t minus tau I can write here as h of t minus tau, where h of t is the impulse response of the system. In terms of continuous, h of t; in terms of discrete means h of n. Then y of t is going to be integration minus infinity to plus infinity x of tau into h of t minus tau into d tau. Therefore what I can write, y of t is going to be x of t convolution with h of t. This equation, and in terms of discrete equation, you have to remember these two formulas will be using now onwards in repetitively. We are going to use of this when going to derive the properties of the any signals. Further we'll be using of these two equations for continuous and also for the discrete. Remember this part. Okay. Okay, we'll go with the one problem here. Here it is given a problem, that is a discrete time LTI system has impulse response h of n as shown in figure. Using linearity and time invariance property, determine the system output y of n if the input x of n it is given. Okay, here the signal is given, that is x of n is going to be 2 delta of n minus delta of n minus 1. Here the x of n is of, here at minus 1 it is having 1, at 0 it is 3, at 1 it is 2, at minus 1 2 it is minus 1, at third position it is 1. It is having the signal like this. First we will write what is our x of n signal. X of n signal is of 2 delta of n minus delta of n minus 1. What I can represent this signal? I hope you are remembering how we are going to done the operation for the delta function. Okay, here it is written directly. Here 2 delta of n. Delta of n is of only at 0th position it is having at 1, right? This is our delta function, delta of n. Okay, here the amplitude is going to be multiplied as 2 for that reason 2 at 0. Then it is shifted by 1 position. Yes, delta of n is shifted by, if it is at 0 it is shifted by 1 position. Okay, here amplitude is 1 only. Then it is of a negative sign, means it is coming in the negative way, means at 1 it is having minus 1. This is what we got. This is the x of n signal we have to perform for this. Then x1 of n, x1 of n is of this one. Okay, take that. This is the impulse response is going to be taken. This means x1 of n is going to be multiplied with the this function. Okay, what I can go here at the 0th position it is having 2, means h of n is going to be, for this 2 is going to be multiplied for each values in the given signal, means 2 into 1 2, then 2 into 3 6, then 2 into 2 4. Position will remain same. Okay, then 2 into minus 1 minus 2, then 2 into 1 is of 2 only. This is, we have to write like this at first value. Then going for the second, that is second sample is of what, delta of n minus 1. That's what you have to take here. Means this I can write as plus of minus delta of n minus 1 is nothing but the same. For that reason here it is taken as plus. I am writing the next part of the signal here. Here it is taken. Okay, then observe here, this minus 1 we have to multiply for the whole signal of here. I will erase this part so you should not get confused here. Okay, this minus 1, it's going to be multiplied for the whole function for this, and shift the signal by one position towards right. Okay, I will this minus 1, if I multiply with 1 means you will be getting as minus 1. Observe here, instead at minus 1 position, it is changed at 0th position. Okay, this is what the change we are going for here. That's what h of n signal is going to be shifted by one position. Okay, based on our delta of n position. Here it is of delta of n minus 1 towards right side for that reason. At 0, minus 1. At 1, it is 3. 3 into minus 1 means minus 3. Then 2 into minus 1 means minus 2. The position is shifted. Observe here, 0. Then at instead at 0, here it will be getting as 1. Instead at 1, here you will get as 2. Instead at 2, here it is 3. And instead at 3, here it is of 4. Next at 2, it is of minus 1. Minus of minus is going to be plus. For the reason here it's going to be plus 1. Here it is of at 3rd, it is going to change at 4th. Then 1 into minus 1 is of minus 1. Okay, next what you have to do? We have to add both the signal. When I add both the signal, I will be able to get my x of n signal. That is, when I adding of these two, I will be getting the same signal what we represented. Then we have to add these two signals. At position, what is the signal? Is of 2. Yes, at 0 is of, here is 6. 6 minus 1 is of 5. Then at 1, here it is 4. At 1, here it is of minus 3. What is, if I add these two, you will be getting as one signal only. Then at 2, here is of minus 2 and here is of minus 2. What is, if I add means minus of minus 4. Then at 3, here it is of 2 and at 3, here it is of 1. 2 plus 1, here it is, you will be getting as 3. Then at 4, here you don't have any signal. At 4, here you will be getting as minus 1. This is how operation we have to perform for this given signal. Okay, we'll stop here. Still a few more problems. We'll continue in the next class.